My name is Atul Bhargava and I'm working as a senior staff engineer at STMicroelectronics. So the technologies on which we are working for range from 130 nanometer to 22 FDX, which is the latest one on which we are working. And the IPs which we are making are for divisions ranging from microcontroller to automotive to space, which is the state of the art which we are working on. So three challenges I would like to enlist over here will go from the smallest bit to the largest bit. The smallest challenge, or not really the smallest in terms of how important it is for the designers, but in terms of the device level. So in terms of device level, when we talk about the analog designs, the biggest challenge is that we have to match the parasitics along with the devices. Now this becomes a challenge which is difficult to solve if everything has to be done manually. So with the help of ModGen, which is provided by Virtuoso, we are able to match the parasitics and the routing on top of our devices and gives a complete good solution in the first go. So that's the beauty of it, and of course we can also save the patterns that we are using in ModGens, and it's a big asset to us. The second challenge that we are facing, we continuously face, is that when we are trying to do our designs using standard cells inside Virtuoso, it becomes a little slower. So we are able to use the capabilities of Innovus without any data translation inside Virtuoso, which gives us the benefit that we are able to do the designs much faster inside Virtuoso without really bothering about data translation. So that's the second benefit that we are able to achieve for the grave challenge that we have. The third challenge that we are seeing is for the full analog test chip design. We are able to do it pretty much seamlessly these days in a much faster way, because earlier the manual efforts which go into the making of these analog test chips is very large. So we are able to use ST utilities for the placement part, and we are able to use RIDE and MST from Virtuoso in order to get this done really fast and in a very quality conscious way. So the overall gain that we are able to achieve in a typical mixed signal IP can be divided into three phases. The first phase is for the device level placement and routing, where we are able to achieve something like a 50 to 55% gain for a typical mixed signal IP. The second one is the digital part of the mixed signal IP, where we are able to leverage the VDI flow and we are able to gain something like a 50% over there. And the final one, when we are taping out the test chip for this analog or a mixed signal IP, the gains are pretty high because we are getting away with the manual efforts, which is something like a 65% gain. Overall, in the total implementation of the mixed signal IP, the gain is somewhere close to a 56 or a 60% that we are able to observe for the advanced technology nodes of 28 or 22 nanometer. So in terms of what's next, first of all, we have been doing all this for 28 and 22 nanometer nodes, and we know that this is not the end of the VLSI. We will go ahead and we will be facing more technology nodes and more of the coloring stuff. And of course, with 18.1, we see that Cadence is coming up with ICADVM, and M stands for metallurgy, which means we will be able to embed a lot of features that we have designed inside ST, which will be a part of the Cadence suite. So that makes the life easier for us, maintenance much better, and we are looking forward to this collaboration going forward and working on this advanced node, where we will be able to come up with methodologies inclusive inside the Virtuoso suite.